This second part is particularly intended for discussion and to be provocative. It's a collection, it's a potpourri of different themes, pretty disorganized, but mostly to throw a lot of ideas that I've heard people discuss in our communities over time, to emit some of my opinions about them, and again, just for people to disagree and jump and vociferously claim that I'm wrong. So I'd like to highlight a couple of problems that I think are emphasize some of the exciting challenges ahead and how far we are from really building good computational models of brain function. So these are some that most of you have seen. I'm going to go very quickly. Current AI is very fragile. For example, it's easy to attack AI with adversarial attacks. There's been a whole industry of adversarial attacks where you can deceive computational algorithms pretty easily. I assume all of you are very familiar with these. Another problem is the notion of continual learning. You train an algorithm to do one task, and then you train it to do a second task, and basically forgets about or largely forgets about the previous task, as opposed to animals that can do one thing and then another, and seemingly and in a flexible manner switch between tasks and do many things. And I think that's also going to be an important and an exciting challenge, to have the same kind of networks that can flexibly perform different tasks without catastrophically forgetting previous ones. And in general, and this is one of the topics that I want to focus on, is again vision and scene understanding, and how far we are from, despite all the claims that there's that vision is solved, and indeed there has been tremendous progress in the domain of vision. I want to highlight still how far we are. So this is an example of a state-of-the-art image captioning system. So it's quite amazing how far we've gone from, let's say, even a decade ago. So in this particular case, if I remember correctly, this is the Microsoft caption bot. It doesn't matter, the claims are similar for many different algorithms. So you can upload any picture. I uploaded this picture, and the algorithm says, I think it's a person standing in front of the Leaning Tower of Pisa. And this is amazing. It's a random picture that I came up with, that I uploaded there, and the algorithm did extremely well. A decade ago, we could not even imagine doing something like this. It's correct. It's a person. I'm pretty sure she's standing. This is indeed the Tower of Pisa. So it's quite amazing. Perhaps it's not too surprising. I don't know how many pictures there are on the web of the Leaning Tower of Pisa. You can probably see the Tower of Pisa from every possible angle under every possible weather. You can memorize pixels and so on. But of course, the reason why this picture is interesting or humorous is not because it's a person standing, but the fact that she's pretending that this is an ice cream, right? And she's licking the Leaning Tower of Pisa. There's a proximity illusion in there. She's holding the cone. There's a lot more happening in here that the algorithm has not been able to detect. I think we're extremely far from being able to have an algorithm that understands what's going on. It doesn't require any kid can understand what's happening in here. You just look at the image, and let's say in a second or so, you can understand what's happening here. I don't think we're anywhere close to that. Do you have a question?
So much as maybe a comment on this. So I think it's not only a lack of knowledge integration. Let's say that we solve this. We endow the models with the ability to understand humor and to see things that are not in their regular context. But this is something that struck me already by Jim DeCarlo's speech, lecture and going on. How well can we even isolate a perceptual modality or some kind of something that we term visual cognition, auditory cognition? We make this isolation and study it and replicate it on a machine, when first anatomically even, of course, IT is going to have projections from the entire brain every time we see anything, but even more so phenomenologically, our experience is always given in a context of memories, of feeling. When I go in the street and I look at a visual patch and I decipher it, I am also fully aware that I'm walking in an urban street and I'm stepping on asphalt and I'm smelling things and I have a memory of cars and stuff. And this is not only a question about building better AI, but even on the level of understanding. You gave three examples of how the brain inspired AI, but the title of the talk was cycle. How well could AI even help us understand the brain with this glass ceiling being there? So lack of knowledge integration, but I think it's even beyond knowledge. This is
I agree with I think with everything you said. I think there's you said lots of things, and so just very quickly, I think you mentioned consciousness. I'll defer on that discussion. Christoph will talk about consciousness tonight. I'm happy to continue discussion about consciousness afterwards. You also mentioned memory and the fact that the brain is not just doing vision or just doing language. I think sometimes in science we do like to do a sort of divide and conquer strategy. I think that is useful. I think that we can make lots of progress in understanding individual processes, even though at the end I agree we'd like to put it all together. I'm trying to argue here that even this problem is still we're still quite far. I do suspect, and maybe here is where I might disagree with you. I do think that this is a solvable problem. I think it will happen. I don't know if it will take us 5 years, 50, 500. I think it's exciting to be young and powerful like all of you are, and there are major challenges and questions ahead. I think it is solvable. I think we will get there. But the point here is that we are extremely far from that. The other question you asked, I think, is about well, even if you have a model that can write the right caption here, that doesn't really mean that it's anatomically correct, that it's actually really mimicking the processes in the brain. Someone was asking me about even if it writes the right caption, it doesn't mean that it's doing it in the same way that I think that there's a lot of interesting questions about how do we know that the model is actually mimicking real computations in the brain. I think we're very far from all of these, and that's part of the point that I will emphasize over and over again now. So generally, I agree with all these comments.
So I was wondering, so what would be the right caption for you to that picture? Because for me, it's really good that it's like trying to, like, you did understand that like the main object in this picture is not the cone of the ice cream, but it's the Leaning Tower of Pisa. Like, I feel like maybe the model is not programmed to output like something the way we want it. Like,
Again, I started by emphasizing how amazing this is. I don't think I think there's been a lot of progress in image captioning. I'm quite impressed by how far the field has gone here. I'm not saying that. I suspect that if I ask people what's happening in this image, very few people would answer. I think it's person in front. I think you will immediately understand there's something more in here. And here, this is an image that we and many other people have used to make the case as well of the same point to that of how far we are. A lot of image capturing systems, they say, I think it's a couple of people standing, or they say they're men with suits and so on. To really understand what's going on here, there's a lot of stuff going on here. You need to understand that that a lot of people are self-conscious about their weight. If you don't understand that concept, you don't really get what's going on. You need to understand that this is a scale. You need to understand that this person is measuring his weight on the scale. That Obama is placing a foot here and exerting a force, that when you push on a scale, you're actually exerting a force. You need to understand that this person is oblivious to what's happening. He's unaware of what's going on. That all of these people do understand the joke and are in on the joke. Maybe they're laughing because it's Obama, and therefore, the boss is doing something. You laugh, right? But I think here, all of these people understand what's happening. He doesn't. There's so much going on in here. I don't think we're anywhere close to building algorithms that can understand this sort of thing. So I don't know if I have a preconceived notion of what the answer should be. I just think that we don't have any algorithm that can understand for an arbitrary image what's really. We have algorithms that can do this sort of thing. I'll let you disagree in a second, but we have algorithms that can do this sort of thing. And again, this is amazing. They can segment objects. They can put different colors. They can detect that there are ties, that there are people in the air, and so on. It's quite amazing. We were not there a decade ago. So we're doing things that are quite extraordinary. But really understanding what's going on in this image, I think we're still quite far.
But what about the other image? So let's say that there's a model that outputs a probability distribution, and it says that with 51% probability that is a person standing close to the Leaning Tower of Pisa, and with 49% probability is a ice cream cone. That will be understanding, in my opinion. It's just a matter of how we decided to parse the output of the network, right?
I still think it's not just a question of saying there's an ice cream cone and there's a person, right? If I put the ice cream cone 10 degrees of visual angle to the left, the picture is not funny anymore, right? So you need to understand the cone matches exactly with the Tower of Pisa, that her tongue is licking, right? I think
Yeah, but that's really close to like what the human experience of an ice cream cone is, and the human experience of a funny picture is. And why do we want this network to basically output something which is so close to like what the human experience of that is, right? Like, I feel
I think for a lot of practical applications, we would love to have systems that understand the world and understand what's going on out there, because we may want to build robots that interact in the real world, because we may want to have systems that understand whether it's a dangerous situation or not. So I think that, again, there's a lot of progress. I think just segmenting an image is very laudable and quite amazing. When I was in grad school, segmentation was an impossible target. Basically, we didn't have any. You could fool segmentation algorithms very very easily. Now we're doing amazingly well. I think scene understanding what's going on, transcends all of our best instance segmentation algorithms. I think there's more to understanding what's going on than just labeling objects. Right. Well, you can continue to add that. Yeah. So you can ask, for example, is this a reflection? Again, you could potentially train algorithms to understand reflections, and you train them specifically to do that sort of thing. In most algorithms, in this case, they don't. Let me just show you, and this may be sort of the somebody sent me these. Is Martin here? So Martin sent me these. This is Flamingo. It's one of the latest DeepMind models. They actually use this image. I don't know if the font is large enough for you to read. Can you read anything? No? Yes, no. The ones in the back, no. The ones in the front, yes. Okay. So this is a dialogue between a human. So the human is in blue, and Flamingo in gray. First, it starts with a caption. So Flamingo says, "This is a picture of Barack Obama. He's a former president of the United States." Again, this is quite cool. They detected that Barack Obama is there. Depending on how you see it, you can say, well, that's impressive. Again, that's an accomplishment. There are zillions of pictures with Barack Obama. I don't know exactly how Flamingo was trained. I'm guessing that they saw zillions of pictures of Barack Obama, but that's great. They recognize. And then they say that the person says, how many people are there in this picture? And it says there are at least 5 people in this picture. Again, this is quite impressive. Where was this picture taken? It was taken in a school. That's pretty good. How many mirrors are there? There are 2 mirrors in this picture. So it can detect mirrors. I don't know if they understand reflection, but they can detect mirrors. What is the person standing on? The person standing on a rug. Well, here the Flamingo didn't get it. So the person says, he's standing on a scale. And Flamingo says, I think you're right. I don't know how much value there is in that, but that's already a little bit fishy, right? But okay, whatever. And then the person said, what is he doing? He's looking at the scale. What is he doing? He's looking at the scale. Where is Obama's foot position? This is pretty specific. I don't know how Obama's foot is positioned on the right side. So first of all, I'm always suspicious when people show me this kind of thing. I'm always suspicious. Well, maybe they train specifically with this image or something. I don't know what they're doing. So I have no idea. This is just a picture that Martin sent me, because I always claim that machines cannot understand humor, and Martin thinks I'm wrong. And so I don't know how this was trained, but it's pretty impressive that it says Obama's food is okay. So what happens as a result? The scale shows a higher weight. This is amazing. I think that this is quite extraordinary. Again, I don't know. Maybe they trained the system with millions of pictures of people putting their food on a scale. I have no idea what transpires really behind the training of Flamingo and how this was done. To the extent that this is an honest, real algorithm, this is quite spectacular. And then, is the person on the scale aware of it? I think he's not aware of it. I don't know. This was 50-50, but I got it right. Flamingo got it right? And then the person says, this is the human says, do you think that's why people are laughing? And Flamingo says, I think so. So some people interpret this to say, well, Flamingo understands humor. They understand exactly what's going on in this image. It can explain. Of course, most of the work here is done by the human who's asking questions and leading from one place to the next and so on. Despite that, to the extent that this, again, I don't really know what's happening behind the scenes and how exactly this algorithm was trained, what kind of images are in the training set. I always like to see when people show algorithms, I always like to see what's in the training set, what's in the test set, how different they are, and so on. But if we take this at face value, I think this is pretty impressive. It's pretty amazing. It doesn't convince me that Flamingo understands humor or this image. You still need a human to lead the whole thing. But I think it's quite impressive. It's fun.
I think one interesting point here is that, for example, you versus Martin, I guess, there are always believers and people who are skeptics, right? In this technology, in some sense. I think so all of the parsing that we've done of the scene in terms of when you press it, the weight increases, or that's an understanding that we have in terms of a certain language we have of parsing a scene, of understanding the context, of understanding physics, all the concepts that are included, right? Those haven't been disambiguated in this conversation, so it remains unclear if the system has understood this. So I guess I have one question, which is, do we necessarily need to have the same structure of understanding for us to be satisfied? And the second is the problem that the structure is not being picked up, or is that we don't have the ways to probe and disambiguate it out from what has already been learned in these representations?
Yeah, I agree, and again, I'm trying to present a balanced view here. I'm neither a complete believer, neither I'm generally skeptic in nature. But I think I'm trying to say yes. There's a lot of amazing things in current algorithms. There's also a long path ahead. Nothing very deep or profound. Just trying to point out that that it's very exciting. All the kind of things that you guys can do and you are going to discover in your lifetimes. I think we're going to see profound, amazing change. There's still a lot to be done here. It doesn't have to be exactly the same structure. It doesn't have to be exactly the same answers that human would be. There are lots of problems in the real world where alignment is useful, where we really may want to align AI and human. For other problems, we may not. I think it would be very interesting for a lot of reasons to be able to have machines that can understand visual scenes or language or in the way humans do for a lot of real world applications. So my claim here is that I think understanding graphical humor is still quite basically impossible. If you do rigorous tests in a systematic way, as you were pointing out, and you control for all kinds of different variables, and in fact, we started doing that. So if anybody's interested, we collected a large data set of graphical humor. We have a lot of images. And then we have either human ratings, or you have people swiping right if it's funny, swiping left if it's not, etc. And so we have human rankings of what people consider to be funny or not. And then we try to use state-of-the-art algorithms and train them and so on. And basically, they're clueless. I think it's very, very hard. I think this is, in my mind right now, still almost an impossible problem. I think it will be solved eventually. But to really understand what's going on and why a particular image is funny or not, I think we're still a long way away from that. And just to clarify, there's something more or less universal about humor, meaning that most people agree, but not entirely, right? So some people may find this picture to be super funny. Some people may find it not to be funny at all. It depends on culture. It depends on age. It depends on what you know about the world, etc., etc. But we can say, well, can we have a machine that can understand humor from people in Argentina, or people from 20-year-olds or 40-year-olds or 15-year-olds. You can define the problem in whatever way you want, but regardless of how you define it, my main argument here is that we're still very far. And this is just one example of a very simple sort of visual discrimination, not very simple, of a visual discrimination task where I show you a picture, you have to say funny, yes or no. And I think that the reasons why an image is funny are so complicated, and we don't have good ways of thinking about how we can teach machines all of the nuances and complexities that lead to categorizing an image as funny or not. So this is for me one very salient example of how far we are in terms of really having algorithms that can really have any kind of decent understanding of a scene.
I think a lot of the issue that problems that current AI are really far from human is no longer like a single modality perceptual problem anymore. Like, for example, understanding humor from an image, it requires a lot more than just like being able to understand the scene composition, what objects are, and then their relationship with one another. Instead, it requires the model to understand like the social, cultural context. And just currently, we do not have an integrated like model that can like learn like sorry, a lifetime worth of context that human are able to get. So like I wonder like what are your thoughts on that, and should we like kind of
I completely agree. And we our very simple initial steps to try to get from objects to scenes has been to study the kind of things that we can study, like the famous case of the drunken sailor looking for his keys under the light, because that's where the light is. We started with object co-occurrences. We started with basic aspects that we can manipulate in an image and so on. I agree that a lot of the sort of more distant problems transcend the statistical regularities of the image. They're not just about object co-occurrences. They're not just about basic contextual cues, which is what we have been working on. I think a lot of it has to do with understanding that people are self-conscious about their weight. That's not vision anymore. It's understanding that when you put a cone on top of a cone, usually there's an ice cream, and that people like to lick an ice cream or something. It's understanding that this is meant to be justice, and this is signaling corruption, and so there's a lot of stuff that goes well beyond perception and vision, and I think that's where I think it's very hard. I don't know how we can train algorithms to learn all of the amazing things that we know about the world. So I completely agree. I think that those are some of the big challenges, and that's what this is highlighting. Okay, so this brings me to a question of there have been a couple of papers trying to look at humor, and in my mind, a lot of this often boils down to some sort of overfitting, meaning that the training set and the test set are very similar, and that's how you can achieve. And so the critical question to me is always, how do you actually do cross-validation? And so cross-validation, you have data, you split it into a training set and a test set, and how similar the training set is to the test set is ultimately what dictates performance. So here's a couple of sort of trivial examples. I don't think this is what we are doing right now, but just to illustrate the point. If I take some training data, here's example images from the ImageNet data set, and I change one pixel in each image. Okay, so I just take one pixel and I change that pixel, and I create this test data here. I can achieve 99% accuracy, 100% accuracy in this task, right? Technically, this is cross-validation, right? This is perfectly legal. These images are different from those pictures. They're not the same pictures. I changed them, right? But nobody would claim that this is a major accomplishment, right? This is a pretty trivial version of generalization, right? So this is trivial generalization. It's not It's not very interesting. And this is the opposite extreme, right? And I call this magic generalization. Imagine now I have an algorithm that I train with these kind of images, and now I test it with these kind of images, and I hope that the algorithm will extrapolate from here to there. And I think this is magic. I think this is impossible. I don't think we can train algorithms here and test them there. Incidentally, I don't think that humans can do this either. I don't think that humans can be trained with these images and test them here, or vice versa. I think the reason why many of us have the illusion that humans can generalize is because we've seen so many things. We're so old and have so much experience with the world that we can do these sort of things. We can understand what this is, not because it necessarily looks very much like a penguin, but because we've seen these kind of images before. So I think there's a question about whether humans really generalize and what does it even mean for humans to generalize. I don't think this has been quantified in a rigorous manner. I think that we're overly confident about our abilities in generalization. But in general, I think that this is, I think, almost impossible. This is this kind of sort of jumping from this domain to this domain. I think this is not quite doable. I think in practice, a lot of what we do right now in AI is somewhere in between. It's not here. It's not changing just one pixel, but exactly defining how we do cross-validation and what's different between a training set and a test set. I think ultimately that dictates how impressed we should or should not be by different algorithms. That's why I kept insisting with Flamingo that I didn't know how it was trained. If Flamingo was never trained with anything resembling somebody putting your foot on a scale, I would be very impressed that you can understand that if you put a foot on your scale on a scale, you increase the measurement. But again, I would like to know always what an algorithm is trained on. What's the closest to the test example in the training set?
So on your statement that you don't think that humans can do this, I feel like this is actually something that you could test. I mean, I agree that probably from this training set, humans can't generalize to the test set, but from the test set to the training set, I'm not so sure.
So you think that if a human never ever sees a drawing or a caricature or anything, you think that just from this they can learn to recognize these images?
Yes,
I would be very
mean, based
surprised.
on childhood drawings and stuff like that, I would think that there is at least the potential that this is possible, and I think it's testable because we probably still have some societies somewhere that haven't encountered clip arts.
I'd love to see the data if somebody has done it. I suspect that a lot of the reason we can recognize drawings is because we spent a lot of time. In my case, I suffered a lot as a kid with somebody trying to teach me how to draw. I never could manage it. But a lot of people told me, if you want to draw a house, this is how you draw a house, right? Not because that looks like a house, but that's where you. This is a conjecture, and I'm happy to be proven wrong. If somebody has done the experiments that you're suggesting with people in some remote part of the world that have never ever seen anything, and they can still understand that this is a person throwing something in the trash. And if they've never seen this at all, I would be very impressed. But I'm happy to be proven wrong. And if you think that there's any evidence that humans can do that, I would love to see the evidence. But I don't know who was first. There are 4 hands. Ladies first. Yeah. Okay. Oh, but you have the microphone. Well, okay. Sorry.
So I wanted to point out that humans can humans can generalize from like the left to right, even though they might never have prior experience. But like throughout development, like kids since the day one they're born, they're constantly getting bombarded with like visual input from the world, and then I don't really remember exactly when, but they develop like 3D shape biases pretty early on based on the kind of experience they're getting. So the possibility, like the fact that some humans, like a lot of humans, can generalize from cartoon object to real world object is because we already had a lot of experience very early on to develop these abilities.
But in that case, they've seen the real world, right? So what I'm talking about is never seeing this and only being trained here, or vice versa, never seeing this kind of stuff. And so if you have a lot of experience with the world, then sure, then yes, we can call it generalization. But I mean, there are questions about whether it's supervised or unsupervised learning and so on. But somebody who has always lived in the real world, never seen anything here. the fact that the idea that they will understand this, I'm skeptic. But again, I'm happy to be proven wrong and people show that. But.
Right. And I think it's like if you find people who are not bird expert and ask them to differentiate, to classify different kinds of birds, a lot of people will probably not perform.
Absolutely, you can take humans out of their comfort zone very, very quickly. You show them pictures of pathological images or tumors or discriminating birds, or for those of us who don't speak Chinese characters, etc., etc., etc. When we are taken out of what we're experienced with, we fail quite miserably. So I don't think that I think our notions that humans can generalize are completely overrated. But.
I was hoping to find it and I wasn't able to, but people have done these studies with larger old world primates where they introduce virtual objects that the animal has never seen, and I I forget what the degree of realism is, but then they read out real interactions afterwards because these are toys that they ultimately give for enrichment, and the behavioral signature is that the animals engage more with the real things on first encounter, first shot, behavioral effects skewed by the images that they've been introduced to in a virtual format. So that's, I think, a potential behavioral signature of this evidence generalizing from something that is a caricature to something that is, the actual real manifestation of that thing. But I'm sorry, I can't find the paper right now.
Send it to me. I'd love to see. And again, how different are they? And there are a lot of technical details, but I'd love to see. And the main point I wanted to make here is that how you define cross-validation, I think, is critical to understand and interpret anything about algorithms. But also as a tangential point that I'm not sure how well humans really generalize. But anyway, yes.
Yeah, I just wanted to add some literature things that I've come across. I think you might be talking about the newborn chicks, how they imprint on like virtual objects. Is that what you're trying to say, or no? Okay, that's fine. There are actually evidence suggesting that infants can already represent 3D cues. And that kind of things increase with like life experiences. And also, picture understanding is kind of a very Western concept. There are studies showing that people in Kenya, children there actually struggle with picture comprehension. So I guess it kind of supports your point that it might be challenging for people who are just exposed to real world objects to then understand 2D objects and to learn from those kinds of pictures.
No, I like all these studies. I'm happy to I'm happy to discuss further. Again, I think I love all these studies in infants as well. I think they have to be done carefully. It's always a question of how much exposure you've had to what and how different is the training set from the test set, and I think we have to keep that in mind for any assessment of human as well as machine.
So I think that with respect to the humor example, so maybe it's kind of unfair towards the machine because we are also exposed to the humor things during day-to-day discussions and like text and like maybe like, oh, yesterday I put the foot on the scale, and like maybe there were like, it's a question if there were models that tried to integrate both visual and text to train AI, and then like you kind of consider there's other effects that we are exposed to.
Yeah, absolutely. The point about humor is just pointing out one example of a purely visual task that's not really purely visual, but that I think is very challenging. Absolutely, humans have exposure to all of that. I suspect that if you've never seen a scale, and if you live in sub-tribe somewhere where there are no scales and where weight is not an issue, people will never understand that picture and why it's interesting. And I suspect that if you live in one of those tribes also, you would not understand the one with corruption either. It's a pretty complicated concept. So yes, absolutely, all of this is a product of human experience with the world and seeing similar things and so on. And it is in a way completely unfair to machines for sure. And it's just an aspirational goal for machines. And it's certainly not the only task, as you pointed out. There are many more. This is just one example of something that I think is quite challenging. We talked a little bit with some people in the interval. I want to jump to something different, which I think has elicited a lot of discussion here as well as elsewhere. and has to do with the notion of what do we mean by understanding. And here I think uh, partly following up on what Jeff Lichtman was saying yesterday, and I think Jim may have said something related. I personally disagree with this notion that the neural networks are black boxes. I think that they're perfectly understandable in the sense that we can perfectly well define every single step in there. I think that's what understanding ultimately will mean. I think that's what we will be able to do in terms of brains. So I think that we should avoid language models. I think that language models will only slow us down. I think ultimately an understanding of nature, an understanding of physics, an understanding of science will have to do with writing equations and building models, not with writing stories in English. I think that writing stories is not the way to understand. I know that a lot of people disagree with this notion, and I'm happy to discuss further. I always give the example of quantum mechanics. Jeff actually independently mentioned this yesterday as well. Quantum mechanics is basically a set of equations that has a lot of power in describing aspects of the world around us. Uh, I could write those equations. I don't think I can do that anymore. I haven't done quantum mechanics in a very long time now. But at some point in my life, I could write those equations. I never really understood quantum mechanics. In fact, many people claim that you can never really understand quantum mechanics. So this notion, this romantic notion that there's a map between the world and reality and words, I think that at some point we'll have to abandon that and understand that a real description of nature will have to take the form of mathematics and computational models and not stories. And this is my personal view. I think that that's shared by people like Jeff, maybe Tommy, Jim, and many others. It's certainly not shared by lots of other people in the world. I'm happy to have people disagree and continue the discussion. But I don't think that these are black boxes. I think these models are very primitive. I think our current neural networks fail in a lot of different ways. But I don't think that it's a fair criticism to say that they're black boxes. They're not black boxes at all. We understand perfectly well everything that's transpiring in every single unit in those models because we have the best possible language to understand them, which is mathematics. What people mean often is, well, what I really like to know is I would like you to tell me a story about this, what this unit is doing. This unit is responding to places or to faces, or it's doing, I don't know. These are stories. I think these words are only slowing us down in our understanding. I think in general in neuroscience and cognitive science, a lot of confusion comes about by people using words in different ways and the vagueness of using words. I don't think that that's the way to go. That's a strong opinion. We can take a couple of people who disagree about this, emit your comments, and then I will move on and we can continue maybe later on. I see everybody's raising their hands to disagree, so I don't know who was first. So whoever has the microphone, and then you pass the microphone. I'll give another microphone.
I think I partly agree with that. And I have a question. So here we built the system so it's completely clear to us what the mathematics is here. If we're modeling a natural phenomena, then we'll come up with a model for it. And it seems there. How do we know when we found the right model? Is prediction the ultimate end game for that model then?
Right. So I think ultimately it's often stated all models are wrong, some are useful. So Jeff also alluded to this. You cannot really prove a model. You can only invalidate models. So we should spend more time falsifying models, not trying to prove that our models are right. We cannot really prove that the model is right. There's more and more. The accumulation of evidence suggests that we believe more and more in models. We believe in gravity because there's so much evidence and it works so well as an explanation of things in the world that we almost take it for granted. But it's a model, right? It's these are all models of reality. Some of them are so powerful, so useful, and we have centuries of data validating them and consistent with them that we take them as universal truth, right? But ultimately, I think that being able to make predictions, being able to make non-intuitive predictions takes us a long way. That's not enough. If I have a model that can help me predict behavior, for example, even if it's very accurate, it doesn't mean that that model behaves in the way our brains do. So we want to be able to map the model to actual real neuroscience mechanisms. There are lots and lots of different levels. So if we have a model that can predict a particular task behavior very well, we can stress test them. We can ask, well, what if I do another task? What if I change this? Can I have non-intuitive predictions that I can test? Can I open up the model and ask whether it matches neuroscience and so on? So I think ultimately we'll need all of these different tests, and the more the accumulation of evidence will help us gain confidence in those models. Prediction, I think, is very good. It's not enough. I don't know. You have a microphone.
Yeah. So I think going back to what you were saying about math, I think we do need to make sense of the equation that we write. Otherwise, how do you go on? How do you make progress? Like, for example, in computational neuroscience, you're trying to make sense of neural networks, trying to compare them with the human brain and trying to get inspiration from the human brain, because the human brain is something that at least to a functional level you understand. Otherwise, how do you get like the creative impulse to like make progress in a field if you just have equation that you cannot make sense of in any human, cannot compare to any human experience?
I agree. I think it's an interesting question. Where does inspiration come from? And I'm not sure I know the answer to that. So yes, I think that there are many fields, particularly in some branches of physics now, where basically people are doing more and more mathematics. I know nothing about string theory, but string theory is a very mathematical domain that it's hard to build intuitions about the real world. Quantum mechanics, I know a little bit more about. It's that some of the basic tenets of quantum mechanics are profoundly counterintuitive, and yet we believe in quantum mechanics because it works, because it can predict aspects of the real world. So I would argue that that's what we need to do. We need to take real world phenomena, and those include spikes, those include behavior, those include calcium, et cetera, et cetera. We need to take real data and ask how well do the models explain those observations. And then at some point, we'll have to accept the fact that these are complex phenomena that can be described by complex models that do not map onto words. And I think this has been the path in some of the more mature sciences. And I think it's unlikely that we'll take a neural network and then we'll find, oh, this unit here is the unit of love, or the unit of faces, or the unit of places, or the chair unit, or any other word that you can come up with. No, this unit is doing this. That's what the unit is doing, and it can help us recognize faces or recognize places, or it can help us do language. It can help us do all kinds of things. This network as a whole. But it's not the case that we can have an explanation for this neuron in terms of, oh, that's the neuron that's the intuitive physics. Oh, I don't know, that whatever you want to. That's not the level of explanation that I think is productive, useful. I think it only slows us
down. So I guess one concept like of black boxes here is not necessarily that we don't understand the artificial neural networks that we're working with, but the mapping between model and real brain, right? Like it might be that the black boxes is how do we go from these equations to what is actually happening in the brain? And I guess one question would be, it seems that it's not enough. If we have the mathematical equations, it seems that we still are missing something, right? And that, I guess this is the intuition of the black box here.
I don't think that's what a lot of people mean by black box. I agree with you that one of the problems I think we've had and people are sort of changing that now. A lot of times people build networks and they don't make a commitment to what this means in terms of neuroscience. So now we can try to make such commitments. For example, I can say, this is the retina, this is V1, this is et cetera, et cetera. The problem with making those commitments is that people don't like to be committed because, once you make a commitment, it's very easy to prove that you're wrong. In fact, if you do that, I can show you very quickly that this doesn't really look like V1 in all kinds of ways. This doesn't really look like IT in all kinds of ways and so on. But I think ultimately we will need to make those mappings and those commitments. And we will have to force people who build computational models to say, well, how does that relate to the real world? And some of that may require abstraction, right? So it may require saying, well, in the same way that in physics sometimes we talk about a spherical cow with a point mass. And in here we can say, well, this is a neuron, and we're abstracting away the geometry of every dendrite because we don't think that we need to understand the geometry of every dendrite in order to build this kind of computation. But I am saying that this unit here is a neuron, and it maps onto neurons in the brain. So I think we can make those kind of commitments. We can build models, and I think there will be progress in making those sort of more informed maps between computational models and actual structures. Do those models need to include the 20,000 proteins inside every neuron? I suspect that that's not the right level of abstraction. Some people may disagree. I have lots of colleagues that work in molecular neuroscience that say, oh, those models are wrong because they don't have protein concentrations. I suspect that we can abstract that away. I suspect that we cannot abstract away neurons. There are people who build models that have, a homunculus or an engine, and there are not even neurons in there. I don't think that that's right either. I think this is the sweet spot, the Goldilocks level, where we have actual neurons in there. But again, what's the right level of abstraction and how to map that into neuroscience is an issue of contention that I think was worth thinking about and debating about.
Yeah.
I don't know whoever has the microphone. So pass the microphone and yes, go.
I wanted to ask, because I see a major difference between quantum mechanics and neural networks. And for me, the most obvious one is that in quantum mechanics, there are just 10 equations. Like they may be difficult, the equation itself, but there are just 10. Instead, if I want to write down the equation for ResNet 152, it's like there are hundreds of equations. And then my question is, do you think that in neuroscience there will come a time where we can like sum up everything in a handful of equations? Because for me, understanding is like more like having a shortcut to. You don't need to go through all the computation that ResNet 15 has done in all those layers. You're understanding what it's doing if you can come up with the answer more quickly. And I think that there are problems where this is not possible. So physics is outstanding for me because the system appears to be very complicated, but I can write down an equation, and with like a minor computation, I can give you where the sun will be in 100 years. I don't need to wait for the universe to come up with the computation that is doing integration, all those time steps. I will just know in advance. And I'm afraid. I think that that neuroscience might be like a field where this is just not possible. And I think that there also will be places in physics where this will not be possible. And for example, like when physics starts to become more similar to neuroscience, for example, in material science, and where you will start needing computers to do things. And for me, the best explanation might be just the computer program in itself. Like the understanding is the computer program then.
I think we're saying the same thing. I agree. Ultimately, the model itself is the best explanation that we have. You talked about material science. Fluid dynamics is another good example. We're not trying to look at every molecule and seeing whether each molecule of water, we have some sort of basic equations, Navier-Stokes, for example, that can describe some macroscopic properties. But ultimately, we run simulations because these problems are pretty complex as well. I'm not sure entirely about the number of equations. If I really want to understand this chair at the quantum mechanic level, that there's also a lot of stuff that you will have to write to get there. There are very few equations here. In fact, you could argue that there's only, backprop and dot products and maybe a logistic. That's it. There are three equations. Now, you can say, well, every unit has weights and parameters, and therefore, it depends on what you mean by equations, right? But here you can say, there are 4,096 units, so each one of these has a different equation. But in terms of the concepts of the equations here, it's very simple, right? In fact, the mathematics behind this is pretty trivial, right?
I would agree that the math is really simple here, but I would also say that you don't understand the chair at a quantum mechanical level because you cannot understand it because you would need thousands of very complicated equations, and you don't understand. I don't understand that.
I don't either. I have the feeling that we can map from the properties of chairness all the way down if we needed to. I don't know, but I have the suspicion that that there's no magic, there's nothing particularly mysterious about it. That if we were to get into it, we could get in as much detail as possible. I aspire to have the same thing for the brain. I don't think we. I think we're very far. I agree with you, but ultimately, that's an aspirational goal. That we hopefully we will be able to understand aspects at all levels. Tommy Poggio and David Mark talked about 3 levels of analysis, from sort of the computation all the way to the hardware implementation. I'd like to be able to fluidly move from one level to the other. I don't think we're quite there yet, but ultimately, I think that that's what understanding will boil down to. There's a couple of other people.
So actually, it's a good thing that people get to ask before, because as you can see, the problem is not people that disagree with the idea that the language of science is mathematics, but the people who do agree that this is the language. It just opens a whole box of questions of what mathematics is the ultimate explanation. And I just wanted to make a point to this end. Well, a neural network is a mathematical model by definition. It's mathematical description, as you pointed out. And people could say that the only thing missing, and I think Jim alluded to that 3M++ model of, if you can have any kind of linear mapping, for some reason it has to be linear, but you can have to think about other constraints, from this to the brain, that's it. We solved it. We got a mathematical description. But I think, but what you said before, the problem is that the math is too simple. Like if we would have stopped at Kepler's laws, those were mathematical laws. They described the phenomena mathematically, but we would agree that Newton added to this and made it into a model by the introduction of ontological concepts, meaning maybe the thing that would tell us if we actually moved from just writing down equations describing the system in a descriptive sense is to have concepts, things like momentum, power, acceleration, things that exist only in, so in a way it is language. Like we need to develop maybe that level of abstraction that relates concept to concepts and not only write down mathematics.
I agree with everything except for the last part about language. I think those concepts maybe STDP. So there may be the concepts could very well be backprop. I don't think backprop is the answer, but those could be the big equations. I think backprop is not what's happening in the brain, but it could be that the answer is spike time independent plasticity. This may not be the right equation. I'm not trying to argue these are the right equation. I'm just saying that ultimately that there will be some sort of equation along those lines, and people will say, okay, yes, that's what's happening. If you, I invite you, and I said this before to some people I was talking in the interval. I'd like to invite people to imagine 5 years from now, or 500 or 5,000. What would an answer be to the question of how the brain works? And I think the answer will be something like this. Not this one. I suspect this is completely wrong. But I think that's the general flavor of what it will look like. It will not be 2 sentences in English. That's not going to be the explanation.
No, I'm not very confident with my definitions here. I just wanted to know, maybe you give a clear-cut criterion. Like I think, like historically, it always came with the advance of, I don't know, if you even closer, so thermodynamics. So you have to come up with entropy. You have to come up with. So I think that would be like maybe an external criterion of knowing that we're getting close. Maybe you have like a better, because all I want to say is that saying mathematics doesn't cut it, in the sense that it's a whole spectrum, and you need to know where you feel confident that there is some kind of.
I'm not claiming I have an answer or providing an answer whatsoever.
I was hoping so.
I'm just suggesting what I imagine the flavor of an answer will look like one day. I certainly don't claim to have that answer. I'm not trying to claim that these particular equations are the right ones. I'm just saying I think that this is what it will look like one day. But no. I know that there are several more questions. Maybe let me do the following. I want to flash very quickly a couple of other things, just again in the spirit of being provocative and making a few other claims. And then I'm happy to take more questions either here or during lunch. I'll also be around later on. And this is a topic I don't think we're going to resolve now. I wish we could resolve it in the next 5 seconds, but we won't. Okay. So keep your thoughts, and I'm going to go very quickly. Okay. So Carlos Ponce is going to give a talk, I think in about 10 days or so, This is just a comment that the current models fail to generalize. They don't really generalize very well. I'm going to skip this. If people are interested, so all of these models where we try to feed neuronal data, we can do so reasonably well. But when we take the models out of their comfort zone, they don't generalize well. This is just basically the same idea. A lot of the semantics that we use to describe neuronal tuning functions, for example, the notion of phase cells, I think that there are major oversimplifications. And here's a study where we are claiming that neurons encode non-semantic features. I'm going to skip the details in the interest of time. I think it's undoubtedly the case that we need much more of unsupervised learning as opposed to supervised learning in building neural networks, and there are many efforts in this direction. By and large, animals learn by pure exposure to the world without supervision or with minimal supervision, and I think this is another rich area that needs to be exploited much more. This is just one basic attempt by this person here, Bill Lauter, to try to build a model that can predict the next frame in a video sequence, and showing that purely from these self-supervised signals, one can build networks and structures that can be quite useful. There's much more to be done in terms of unsupervised learning. I think one or two more quick things that I wanted to flash here. I'm tired of hearing lots of people always saying, well, humans are unique because, and there's all this anthropomorphic notion that we think that we are so amazing and so special. If you have any thought about why humans are special, send it to me. I collect them. I have them. One day I will write an article with all the claims that you name that. They're all. There are some people that think that language is unique to humans. Some people think that humans are the only conscious people, the only ones that have free will. I guess it depends on what you work on. If you're an artist, you think that humans can do art, and so depending on what you're on what you work on, you can always complete this sentence in a lot of different ways. I believe in the continuity of evolution. I don't think that we are that interesting or that special. I think we have to understand humans for a lot of reasons. I alluded to those at the very beginning. But I think that machines eventually will be able to accomplish many, if not of most of the tasks that we can accomplish, and also that animals are at least as intelligent as we are. I used to joke and add, humans are the only animals that wear Nike shoes. And then, okay, so this is about the continuity of evolution. And then somebody sent me this picture, just proving that even this statement, which seems pretty obviously true, even that is complete nonsense. So anyway, I think a lot of these, a lot of people believe in many of these things. I suspect that most of these things are just wrong. That there's nothing special about humans. Animals can display a lot of these properties. Are we different from animals? Yes, for sure. In the same way, I suspect that all of these will be reproduced in machines one day. Here's a robot wearing Nike shoes as well. So the last point I want to make, again, just to stimulate discussion, one of the last remnants of human usefulness in this world for many people is the notion that humans can be creative. We can create things. We can come up with new theorems and prove them. We can create art. We can create lots of things. And this notion of creativity, I think it's also being undermined now by the development of better and better algorithms that can also create different forms of art. So some of you may have seen this picture here. So this is a generative algorithm that can create art. This was sold for something like $500,000 or so. If I didn't tell you that this was created by a machine, probably a few years ago, you wouldn't have been able to tell. Now, I think most of you are familiar with lots of algorithms that can draw and create things that are certainly better than the way I can draw, and that they are on par with some of the best artists out there. There's a lot of interesting discussions around this. This is another example in the context of music. Happy to discuss more with people if they are interested. Here's the link. This is a machine that was trying to create Bach-like classical music. They show you here two pieces of music. I think it's pretty hard to distinguish which one was created by a machine, which one was created by human. So I had a bet with some of my colleagues. I suspect that in the next 10 years there will be a song in the US top 40 Billboard list of the best songs in the US that will be completely created by a machine. That there will be no human intervention whatsoever. That the machines will be able to create music, and not only create music, but it will be some of the most listened to songs and some of the best songs in the US will be completely created by a machine. There's a lot of questions about what creativity really means, because when we go down this road, a lot of people say, well, that's fine. So you can sort of emulate Bach, but you cannot really come up with a new Bach or something completely new in music. I don't know, Bartok. I hate Bartok. I don't like Bartok. For those of you who know what, it's a new way of doing music. It's dissonant. It's different. I don't like it, but it doesn't matter. That's my taste. But can you really come up with a Picasso? Picasso changed art, right? So he sort of went in a new direction. And that people claim is hard. It's not just creating art in this way, but actually coming up with a completely new way of thinking about visual art or a completely new way of doing music. And people claim that's a human thing that machines can do. I don't know exactly how to evaluate that. I don't know whether art or creativity happens in a vacuum. You can say the same thing about science, right? So yes, many of us can take a neural network and add one layer and improve performance. But can you really come up with a completely new idea that nobody has ever come up with before? So first of all, I'm not sure that humans can really do that and really can do something completely different. But even if we can, I'm not sure whether that will be able to, whether we can reproduce that in machines or not. But at least at this level, I think that the notion that creativity is unique to humans or unique to animals is being contested, and I suspect that we'll see more and more of so-called creativity by machines in the not too distant future. Again, happy to be proven wrong and happy to have people disagree with me on this. So that's all I wanted to say for now. I'm happy to continue the discussion. I tried specifically to have several claims at the end that are pretty provocative for people to disagree with me. And if you don't agree with my definition of understanding, or you think that humans are special in terms of creativity or anything, or any of the claims that I made, I'm happy to hear your comments and continue the debate. So that's it.